we go. All right, this is being recorded. Let's dive into it. We're in section 6.1. So 6.1 is on systems. Chapter 6 is on systems of equations. And then 6.1 is systems of equations in two variables. Okay. So a system of two variables, in order to solve these, typically you're going to need two equations. So a lot of times you'll see it just two equations bound by kind of a curly bracket looking thing. The first one was better. So perhaps this one equation and another equation. And we're going to talk about ways to solve these methods. And let's start with defining what a solution is. A solution of a system of a 2x2, so we'll call it a 2x2 for now because we're just going to deal with a set of two equations with two unknowns. So a solution of a 2x2 system is an ordered pair. So whatever that x, y, and y value is, that solves both of those equations. So, for example, we might be asked, is 1, -2 a solution to that system of equations? And to find out, we would just plug it in. So in the first equation, we want to call this equation 1, plug it in. And if it's a solution to it, then it's a solution to that, but it may not be a solution to the system. We have to check both of them. So we're going to plug in the x value in for x, that's 1, the y value in for y, and we can see this fails already because 1 minus -2 is the same as 1 plus 2, so that becomes 3. So that fails already, and once it fails one, then it's not a solution. And you don't have to check the other one. So no, it's not, and that's that. So is 2, -3 a solution? Again, so we'll just plug it in into each one, plug it into the first equation, 2 in for x, minus -3 in for y, and that is true, because 2 minus -3, that's 5, so this is true. But I have to check both of them. So I'm going to check equation 2. 2 times x, but x is 2, plus y, which is -3, should equal 1. And 2 times 2 is 4, plus -3 is the same as -3, and that is 1. That's true as well. So then the answer to this is yes, it is a solution. So let's take a look and see. The first method that we would play around with here is to graph. So let's graph. We already have the solutions, but let's graph this system that we were just playing with of x minus y equals 5, and 2x plus y equals 1. Now I can manipulate this system in any way that I want, as long as I don't change the equations. I can use the addition principle. I can use the multiplication principle, things like that. So on equation 1, this guy right here, I'm just going to move the x to the other side. So I'm going to like subtract x, which leaves me with negative y equals negative x plus 5. And then I want to get rid of this negative over here. So I'm going to multiply everything by negative 1. And so this becomes y equals, the negative 1 distributes through the right-hand side, so that becomes x minus 5. And then on the other one, I'm going to just minus 2x from both sides. So subtracting 2x leaves me with y on the other side, negative 2x plus 1. I'm going to leave it just like that, because now I have both of these guys in y equals mx plus b, which is the slope-intercept form, right? And it should be easy to graph this. All right, we already know the solution, right? That we already know a solution. That may not be the only solution, but we have a solution of 2, negative 3, right? Well, when we graph that, that should be where these two lines intersect, because that point, if they intersect, that's where a point is that is on both of these lines. So if I graph the first line, which I put into y equals mx plus b, so that I have a intercept of negative 5, so that would be here. And then a slope of 1, right? If there's not a number in front of the x, that's a 1. Right? But that 1 is the same as like 1 over 1. So you go up 1 over 1, there's another point, up 1 over 1, there's a point, and so on and so on. And so we've got that as our first line. Okay. And then I'll graph the other guy here. I've put into y equals mx plus b form, so I have a intercept of 1. That's there. And a slope of negative 2. So that means I go down 2 over 1. So I have another point, down 2 over 1. And these 2 points right here, that happens to be that value of 2, negative 3. And that's the only place that's on both of these lines. Good enough. Oh, you suck. There we go. Oh, all right. I give up. There we go. All right, so there's the 2 lines. They only touch at 1 point. They touch right there at the point 2, negative 3. So there is only one solution to this equation, and that's it. So the graphing method has its limitations. If your answer is not a nice integer pair like 2, negative 3, like say, for example, I had some system and the solution was like 2.25, comma 1.03, right? There's no way I could graph that and have any idea that the y value is 1.03, or even I'd have a difficulty guessing that the x value is 2.25 as opposed to say 2.3, 2.2, right? So graphing is okay in most situations, but not always. If it's not an integer value, or if it's just something that's not easy to graph, then sometimes it's not the greatest thing. But you can see by the graph, this shows us here that there's one and only one solution, and that is this instance right here, right? There's 3 different types of graphs we'll end up running into. If they intersect at 1 point, then there is one solution, right? But you might have a graph that intersects everywhere. The two lines are the exact same line. In that case, the lines are identical, so you have infinitely many solutions. It's every single point that's on that line is also the point on the other line because it's the same line, right? But in this one in the middle here, if they're parallel lines, they're never going to cross, and so there is no solution. So you've got three options here. You're either going to come down to one solution, no solutions, or the entire line is the solution. But like I said before, the graphing is not ideal. Sometimes it's very hard to get an answer for graphing. So let's move to another method here. And this is the substitution method. And so we're asked to solve something like another system. Let's say, in fact, let's do the same system. Let's do x minus y equals 5 and 2x plus y equals 1. Right? Now, the idea in the substitution method is to isolate a variable and then substitute its equivalence into the other equation. So I want to pick out one of these variables, and in this guy, I'm going to pick out this x because it's going to be the easiest to isolate him. All I have to do is add y to both sides of this equation, and I've got x. So if I do that, this leaves me with x equals y plus 5, or 5 plus y, either way. But since now I know that x is equivalent to being 5 more than y, wherever I see an x, like in this other equation, I can replace it with that expression of y plus 5. So I will. And I want to make sure to put it in the other equation, because if I put it back into the same equation, it's just going to boil down to something that's true all the time. So I'm going to use the other equation, and I will. So 2 times x, but x is y plus 5, plus y equals 1. Now I have one equation with one variable, and I'll just solve it. Start by distributing the 2. That gives me 2y plus 10 plus y equals 1. Combine my 2y and y to give me 3y plus 10 equals 1. Subtract my 10 from both sides. This gives me 3y equals negative 9. And if I divide by 3, I've got y equals negative 3. And that's half of my solution. What I want to do now is take this, and I know what y is equal to now. So in any one of these equations, it doesn't really matter which one, I'm going to take this and plug it into the y value. So I'm going to plug it into that first one for no obvious reason, just because it's going to look easier to deal with. If I plug it in there, then I have x minus y, which is negative 3, equals 5, or x plus 3 equals 5. And then I'll subtract 3 from both sides. And there we have it. I've got the same answer, and I just didn't do it graphically. Just did it mathematically with the substitution method. So that's the second method, substitution method. It's a little bit nicer than graphing, that's for sure. But we'll see that it also has its limitations. Let's take a look at another example, though. Our examples are not great. Here we go. Okay, third one. So x minus 2y equals 7, and x equals y plus 4. So this one looks like it was almost set up to be a substitution method because x is already isolated. So I'm going to take that y plus, this isn't the same question, is it? No, it's not. All right. So I'm going to take this y plus 4 and replace the x in the other equation with it. So x, which is now y plus 4, minus 2y equals 7. Combine my y terms, y and minus 2y is just minus y. Get rid of that 4 by subtracting it. And then multiply both sides by -1, and I get y equals -3. Now that I know y is -3, I'm going to take that value and plant it into any one of the y's. It doesn't matter. I'm going to plug it into there. So this will give me x equals y, which I know is -3, plus 4. And so x is equal to 1. So I have my solution. It's the ordered pair 1, -3. Where this limitations come up, or when you're asked to solve things like, let me find one. There we go. All right, we'll do this one. Two x equals 5 minus 3y. And 4x equals 11. Minus 7y. So it's not that bad. But the first thing that you want to do is isolate one of these variables. And it's hard to do that because no matter which variable you try to solve for, you're going to end up with a fraction, and people typically hate fractions, right? But if I'm going to go through and do this with the substitution method, I still can. I can just solve, pick one, right? This is already solved for 2x, so all I have to do is divide everything here by 2. And so this becomes x equals 5 over 2 minus 3 over 2y. And it's this expression right here that I'm going to plug into the x over here. So that turns into 4 times, instead of x, all of that, 5 over 2 minus 3 over 2y equals 11 minus 7y. But if I distribute this through, 4 times 5 halves, that becomes 10. 4 times minus 3 halves, that becomes minus 6y. So not the worst. The fractions went away after one move, perhaps. Now I just want to get all of my y's onto one side, so I'm going to add 7y to each side. And since I am moving my y's to the left, I'm also going to subtract my 10, move my non-y terms to the right. And in fact, that does it for my y's. Y is equal to 1. I'll just take that y equals 1 and plug it into one of the original equations. perhaps this one up here. That's going to give me 2x equals 5 minus 3 times y, but that's just 1. And so then I've got 2x equals 5 minus 3, which is 2, and so x equals 1. And so my solution is x equals 1 and y equals 1. So the ordered pair, 1, 1. Okay. So that's sort of the limitations on, one of the limitations on substitution is sometimes you just can't get a nice value to solve for, to isolate. So what we'll do here is we'll move on to the next method. And that next method is called two things. It's either called the addition method or the elimination method. Okay, we'll grab one for this guy. There we go. All right, so if I had a system that looked like this, say 4x plus 3y equals 11, and negative 5x plus 2y equals 15. Isolating one of these variables would be difficult. I'd end up with a fraction no matter what. I would just have to decide if my fractions were all over 4 or over 3 or over a 5 or over a 2, right? Whichever one of those is the least horrific fraction to be dealing with. But graphing it is also not very nice because these don't turn into nice y equal mx plus b's. They don't turn into, it's not easy to find your intercepts, your x-intercepts or your y-intercepts for any of these. And so the addition method is typically the easiest to deal with. So I'm going to pause here because I want to show you one before I do this one. Let's go back to that very first one. So we're gonna stick a pin in this guy. We'll come back to it. We're gonna go back to this 2x plus y equals 2 and x minus y equals 7. We'll show you what it is on this one first, and then we'll go play with the other one. So recall in the addition method, or the addition principle of equality, if I have A equals B, then I can add C to the left as long as I add C to the right, right? But if C is equal to D, then it doesn't matter if I add C to the right or if I add D to the right. Right? And so that is to say, if I start with an equality, A equals B, I can end up with A plus C equals B plus D as long as C is equal to D, right? But I have equations right here. X minus y is equal to 7. And so let's look at this equation, the first equation here. This equation right here, this is getting pretty messy, and I apologize. I'm going to clean it up a little bit. All right, we're going to deal with this first equation. To the left of it, I'm going to add this x minus y. But on the right of it, I'm going to add 7, which I can justifiably do because those two things are equal. X minus y is equal to 7. So if I add x minus y to the left and 7 to the right, what happens? Well, I get 2x plus x, which is 3x. And I get y and negative y, which is nothing. It's gone. And then I get 7 plus 2 is 9. And in one move, I've eliminated y. And one more move, I've solved for x. And that's very simple. There's no graphing. There's no the substitution method. If you recall, we just did here. It took us all of this work right here. Oh, this work right here just to get to that, right? Just to get to our first variable's value. And so it's much quicker, it's much faster, typically cleaner. But there it is, x equals 3. And since I know x equals 3, I'm then going to take that and plug it into one of these or the other. It doesn't matter. 3 minus y equals 7. Subtract 3 from each side, and I get minus y equals 4. Multiply each side by -1, and I've got y equals -4. Right? Had the same answer that, oops. Oh, what did I mess up on? X is 3. Is this the same? Oh, it's not the same. Yeah, it is. 2x plus y is 2. Oh, it's not the same. All right. Well, it's not the same equation. So just kidding for a minute. All right. But we're done. All right. Sorry, I was trying to compare to the last one. I thought I had the same equations, but the numbers were different. So my answers are different. But that gives me my solution of 3, -4. And I'm done, right? So let's go back to this first one that we said we'll come back to, right? The idea is this right here, that I have a y and a negative y. I have one of the variables that has the same but opposite coefficient in front, right? And I don't have that here. But I can use the multiplication principle of equalities to manipulate these to get it there. And so I'll start by, my y values are smaller over here. So if I multiply the left and the right-hand side of this equation by -2, and then the left and the right-hand side of this equation by a +3, that'll specifically give me this -2 times 3 is -6, and 3 times 2 is +6. That'll give me a positive 6y and a -6y, and I can eliminate my y. So my new equivalent system is -2 times the first one, so that's -8x, minus 6y equals -22. On the bottom one, I'm multiplying 3 through everything, so it's -15y, or sorry, x, plus 6y equals 3 times 45. 3 times 15 is 45. And make sure you multiply the right-hand sides as well, because it's the multiplication principle we're using. We have to multiply both left and right-hand sides. But I've got it. I can combine these, right? -8x and -15x ends up being -23x. -6y and 6y cancel. They're gone. And then 45 minus 22, 23, pretty convenient, because I can divide by -23, and I get x equals -1. And I'm halfway home. Now all I have to do is take that x equals -1 and put it into one of the original, either, and it doesn't matter because I really have 4 equations now that I can use. It just depends on which one looks the nicest. So I can use one of the 2 originals or one of the 2 after I've manipulated it. But typically one of the originals will have smaller numbers, so I'm going to choose that. And I'll just put it into this original equation of the second one. And so this gives me -5x, or -5 times -1, plus 2y equals 15, or 5 plus 2y equals 15. Subtract 5 from both sides, and that gives me 2y equals, excuse me, 10. And divide each side by 2 gives me y equals 5. And I'm done. I've got x, I've got y, I've got my ordered pair solution. All right, let's look at a couple of things to be concerned with. Let me clear that out because it's lagging a bit. Let's look at this guy. Two x plus 3y equals 6. And 4x plus 6y equals 12. Okay, if I'm using the elimination method, I want to multiply potentially both equations. It doesn't always have to be. But if I just look at my x's, I can multiply this top one by -2, because that -2, when I multiply it into this x, is going to turn it to a -4x, which I'll use to cancel with the positive 4x. So my new system here becomes -2 gets multiplied, so that's -4x minus 6y equals -12. And then the other guy stays the same. The second equation stays how it is, 4x plus 6y equals 12. And if I combine these now, I've got -4x and 4x is 0, -6y and 6y is 0, and -12 and 12 is 0. But this is a true statement. Right, everything's zeroed out, but it's still true. It's a true statement, and not only is it true, it's true no matter what. Right? And you have to be careful with the term no matter what, right? But that just means that these guys are the same line. So there's an infinite number of solutions, right? And that's not to say that everything's a solution. It just means that there's an infinite number of them. If I graph these two lines, I don't know what they look like, but let's see, x would be at 3, y would be at 2. So they both look like this. That's a terrible line, and I missed both of my spots, but it doesn't matter. It's whatever's on that line is a solution, right? So again, it's be careful when you say infinite solutions. Don't just say everything is a solution, because it's not. Some random point like over here is clearly not a solution. It's not on either line, right? But that is the same line, so we have infinite number of solutions. Now let's look at this one. X minus 3y equals 1, and -2x plus 6y equals 5. So again, I'm going to play with the x's, because all I have to do is multiply the top one by a +2. If I multiply this entire equation by a 2, I get the new system of 2x minus 6y equals 2, and then -2x plus 6y equals 5. And if I combine those, the x's cancel out, the y's cancel out. That just gives me a 0 on the left-hand side, but I get 7 on the right-hand side, and this is false. It's false no matter what x is. It's false no matter what y is, right? And so if I plug in graph of what these guys look like, this is something like this is the first one. And then the second one is something like that. And so the reason that we get down to a false is because these guys are parallel lines. And there will be no solutions here. All right, let's grab a application here. All right. At Max's Munchies, we have caramel corn worth $2.50 per pound is mixed with honey roasted mixed nuts worth $7.50 per pound in order to get 20 pounds of a mixture worth $4.50 per pound. How much of each snack is used, right? So there's a lot of words here. What are we going to do? Well, let's start by identifying. We've got caramel corn. So I'm going to say that X is the number of pounds of caramel corn. And we've got honey roasted mixed nuts. All right, Logan, you've got a question? All right, no problem. All right, then we've got honey roasted mixed nuts. So we'll label that as Y is the number of pounds of honey mixed nuts, right? And I can create equations, right? There's a couple of things that I've got, right? The caramel corn is $2.50 a pound. The roasted nuts are $7.50 a pound. But altogether, I'm combining the number of pounds of caramel corn and the number of pounds of honey roasted nuts to get 20 pounds of nuts. That first equation is the number of pounds of caramel corn added to the number of pounds of honey roasted mixed nuts should equal 20. That's the first equation. First equation is typically the easiest. The other one's a little bit more difficult, but it has to do with the prices, right? If caramel corn is $2.50, then $2.50 multiplied per pound multiplied by the number of pounds gives you the amount or the cost of the caramel corn that's used. And if you add to that $7.50 multiplied by the number of pounds of honey roasted nuts, that's the cost of the honey roasted nuts. So I'm taking the cost of one, adding it to the cost of the other, and it should be the total cost of everything else, which is $4.50 per pound multiplied by 20 pounds. So I can clean this up a little bit, but my system becomes this: X plus Y equals 20, and 2.5X plus 7.5Y equals 90. And that's my system. Now, graphing this system would probably be ugly, especially with this 2.5 and that 7.5. Using substitution, though, is not terrible because I've got this X and the Y in the first equation. I could solve for either one of those and plug it in, right? My personal preference is to use the addition or elimination method, which I don't care if that becomes your preference or not. I'm not trying to push that on you. That's just what I do. But I would do it by multiplying this top equation by minus 2.5. So my new equivalent system is negative 2.5x, which I did specifically to eliminate with that 2.5x below it. Oops. Yeah, plus 2.5 minus, not plus. So minus 2.5y equals negative 50. And then I'm not going to touch the bottom one because I've got the 2.5x. That's what I wanted. And I'll combine left and right. So the x's are gone. But that leaves me with negative 2.5y plus 7.5y. That's 5y. Negative 50 plus 90. And then pretty quickly, I've already got half my answer. And then solve it for x. And there's a lot of times a blatantly obvious one that you want to use because x plus y equals 20. Well, x plus 8 equals 20 is a pretty easy equation to solve for. Just subtract 8 from both sides, and you're done. So then in the context of this question, what does that mean? Well, we said that x was the number of pounds of caramel corn. So to answer the question, we would say that we're going to use 8 pounds of caramel corn and 12 pounds of mixed nuts. Are we okay with that? Any questions on that? Okay. We'll do another one like that in the same kind of realm as that. All right. We've got an airplane. It's flying 3,000 miles from LA to New York, and it's got a tailwind. When it's got a tailwind, it does it in 5 hours. The return trip with the headwind, which is against the wind, slows it down. It takes 6 hours to do. Find the speed of the airplane in still air and the speed of the wind. Now, I didn't on the last time, but on the last question, but a lot of times creating a little chart is helpful. So I'm going to create with the wind, against the wind, and my equation that I have here is distance equals rate times time. So in both of these cases, they're flying the same flight. It's 3,000 miles. Right? And I know that when it goes with the wind, it's going to take 5 hours. And when they go against the wind, it's going to take 6 hours. Right? So those I know. I don't have to do anything special there. But I've got two things happening. I've got the speed of the airplane, which I'll call x. And then I've got the speed of the wind, which I'll call y. Now, when I'm going with the wind, right, I've got this airplane, beautiful airplane. It's going there, and the wind is pushing it along. And so the speed of the airplane and the speed of the wind add together. So when I'm going with the wind, the speed that I'm traveling is x plus y. Now, if I'm going against the wind, then the opposite thing happens. I've got this wind pushing against the airplane, and so it subtracts from your speed, and so your rate against the wind is x minus y. And these two are going to create my equations, right? It's distance equals rate times time, so it's that. Those are my two equations, just sitting right there, waiting for me to write them down. So I have 3,000 equals x plus y times 5. I'm going to write it as 5 multiplied by x plus y. And then I have 3,000 equals 6 times x minus y. I'm going to do my distribution. So I'll write this as 5x plus 5y. And I'm going to move my 3,000 off to the other side just to get it into the same format that we've been dealing with these. So I've got 5x plus 5y equals 3,000. And then the same thing on the other guy gives me 6x minus 6y equals 3,000. Now, all I have to do is multiply one of these, let's say the top by a positive 6 and the bottom by a negative or by a positive 5. I'm just going to get my y's to cancel out because they're already the opposite signs. So I'm just going to multiply the top by a 6 and the bottom by a 5. This gives me the equivalent of 30x plus 30y equals 18,000. And the bottom multiplying by 5, so I've got 30x minus 30y equals 15,000. Combine those, y's are gone. 30x plus 30x is 60x. If I add these together, $33,000, and then I'll just divide each side by 60. So then I've got x equals, and what is that? I don't know. 33,000. $550. So I know x, and then I just have to plug that into one of these guys, one or the other. Again, it doesn't matter, right? Pick the first one, pick the second one. I don't care. I'll do the first one. 5x, so 5 times 550 plus 5y equals 3,000. Or 5 times 550 is 2,750. Excuse me. And then I'll subtract 2,750 from both sides. This gives me 5y equals 250. And if I divide each side by 5, I get y is equal to 50. So again, since we defined the x variable to be the speed of the plane, that means the plane was going 550 miles per hour. And then y was the speed of the wind, which meant we had a 50-mile-an-hour wind. We okay with those for the most part? Okay. Well, that's it. That's all we have for today. So if you have questions, please stick around and ask. Otherwise, I'll see you guys back in the classroom on Monday.